To factor polynomials, we're going to start by talking about removing the greatest common factor. So here in example 1, we have 3 different polynomials. Looking at this one first, I wanted to look at both terms and ask the question of what is the most that we could take out of both. Whatever that is what we call the greatest common factor. I'll abbreviate that GCF. So the way I do this is by first looking at the numbers 27 and 18. The most that I can take out of both of those is a factor of 9. 9 goes into both 27 and 18, and that's the most that I could take out from both. So that's the numbers, but what about the x's? Here I have x to the 4th and x cubed. The most that you could take out from both of those is x to the power of 3. This is the greatest common factor between those two terms. Now to actually factor this thing apart, I'll write the greatest common factor and set up some parentheses. Inside the parentheses, I'm going to write what is left over after you remove this from both of these terms. Let's start with the 27x to the 4th. If I remove 9 from 27, that leaves me with 3 left over. And if I remove an x cubed from an x to the 4th, I'm left with just an x. I'll then put a minus sign, because there's a minus sign right here. Okay, now I have 18x cubed. If I remove 9 from 18, I'm left with 2. And if I take x cubed from x cubed, I would have no x's left over. And this will be my final answer. I removed 9x cubed from both terms, and this is what is left over. It's worth thinking about checking your answer by distributing this back into the parentheses. It should take you back to the answer we have here. 9 times 3 is 27. X cubed times x is x to the 4th, so it worked for the first term. Then I have minus. 9 times 2 is 18. And x cubed times, well, there's just a 1 here, it gives me x cubed, and I know that my answer is in fact correct. This is a good way to actually check your work or reason out what the answer is by working backwards. If I multiply this in, does it take me to what is over here? Let's try this in the next term, the next polynomial, I mean. Now I have 3 terms, but the question is, what is the greatest common factor? This is a little bit more complicated because not only do I have x's, but I also have y's as well. So let's see, the greatest common factor, but we're just going to break it up into steps where I'll first look at the numbers, and then I'll look at the x's, and then the y's. Starting with 30, 45, and 90, the most that I could take out of those is going to be 15. That goes into both 30, 45, and 90, and that's the most that you can take out. Now let's focus on the x's. We have x squared, x to the 1st, and x cubed. The most that you can take out is x to the 1st power, so I'll copy down x. And for the y's, we have y, and y squared. The most that you could take out from all 3 is simply y. It's always going to be the smallest amount that appears in each term. So this is my greatest common factor, 15xy. And our job is to now figure out, well, what's left over after I factor that out from all terms. So 30x squared y, if you take out 15, you're going to be left with 2. Okay, if you take out an x, you're left with an x. And if you take out a y, there are no y's left over, and so we get 2x. Continuing, we get minus. If I take out 15 from 45, I'm left with 3. And if I take xy from an xy, there's actually no variables left over. Okay, now we have 90x cubed y squared. Okay, if I take 15 out of 90, I have 6. If I take an x from an x cubed, I get x squared. And if I take out a y from y squared, I'm left with y. If I distribute 15xy to these 3 terms, it would take me back to this expression here. Okay, one last one. We have 4x times x plus y minus 3 times x plus y. So this one's a little bit weird, but here I have x plus y, and I'm going to treat this thing in parentheses like its own term. It's just one thing. Now the greatest common factor, the way this is written, is going to be x plus y. There's nothing common between 4 and 3 other than 1, which you don't have to write. There is an x that's multiplied here, and there's no x by itself over here, but there is an x plus y that's common to both. So you're allowed to remove that whole thing, even though it is actually two separate terms in parentheses. So what is left over? If you take out x plus y and x plus y, it would leave us with a 4x and this minus 3. And this is the answer. If you think of distributing this whole thing into the parentheses, it gets multiplied here, and it gets multiplied here, taking us back to this expression. So let's use this idea of a greatest common factor in a slightly different way, where we're going to factor the following polynomials. We're going to use a method called factor by grouping. If you look at this very first polynomial, I see I have some like terms in the middle, but more importantly, the greatest common factor between these four terms, well, here I have an x. Well, yeah, if I think about that, what's the most I could take out in terms of the x's? I have x squared, x, and no x's. You can't take any x's out. In terms of numbers, there is nothing common between 5, 10, 7, and 14. So we're kind of stuck. I look at this and the greatest common factor is 1. If this situation arises, I want to try this other method where what we're going to do is still use a greatest common factor, but remove it from the first two terms and the last two terms and figure this out separately. All right, so the greatest common factor for the first two terms is 5x. And the greatest common factor for the last two terms is 7. Let's write that out. For just the first two terms, if I take out a 5x, I'm left with x plus 2. If I distribute 5x to x, I get 5x squared. If I multiply 5x to 2, I get 10x. All right, now let's figure out if I remove a 7 from the last two terms. I'm left with x plus 2. Notice that when we did this, we have this x plus 2 common to both terms. And just like in the previous example, you can now factor that thing out. If we do that, you take out x plus 2, and you're left with 5x and 7. So this trick actually allowed us to factor the polynomial. It just took us a couple of steps. So I didn't take out a greatest common factor from all four terms because it was just 1, but just by using the first two and last two, it introduced a greatest common factor that I can remove from the whole thing. Let's try this again with this last example here. Now we have two variables. Same idea. I want to take out the greatest common factor from the first two terms and the last two terms. Let's see what happens. The greatest common factor for the first two terms is 2x squared, and the greatest common factor for the last two terms is going to be 4y. Let's see what we get. If I take out 2x squared, I'm left with 2x minus 1. And if I take out a 4y, I'm left with negative 2x plus 1. This didn't seem to work. I mean, okay, I have 2x minus 1, but here I have minus 2x plus 1, so that's not good. If this happens, I can now take out a negative from both of these terms. So I'm actually going to pull this negative out and place it here. This will become positive, and this will become negative. So if this happens, I'm going to factor out a negative. I'll put factor out negative 1. In doing so, I get 2x squared times 2x minus 1. I pull out that negative, and it changes the sign on everything in that second set of parentheses. I now have a common factor that I can remove from both of those terms. I can take out 2x minus 1, and I'm left with 2x squared minus 4y. And I'll treat this as my final answer, kind of like this one up here was factored in two pieces, and that's it.